Howdy, y'all. Dr. Rob Parks here. This is the first lecture in the ASTR 124 Introduction to Observational Techniques class. I do apologize for posting this late. Next videos will be posted every Sunday moving forward. Today I'd like to talk about coordinate systems. Coordinate systems are based on a variety of different things, which I'll get into in a second. But effectively, in order to have a coordinate system, you first have to have something to put it on. And this is commonly referred to as the celestial sphere. This was an invention by the Greeks, who actually envisioned this as a physical object. This is a sphere that is encompassing the Earth, where the dots correspond to, where the stars, planets, and everything in the universe occupies a space on that. We now know that this is an abstraction, that a physical sphere does not actually envelop the Earth, but is still a useful tool. I'm going to be going over four major coordinate systems today, those being horizontal, equatorial, ecliptic, and galactic longitude. And it basically depends on what you're studying effectively. The horizontal system was first developed by Hipparchus, where he was able to differentially tell the difference between that star is positioned here as opposed to that star which is positioned there. So he could tell the position of one star relative to the other, but as I'll get into in a moment, he could not determine an absolute coordinate system based on the horizon system does not provide an absolute reference frame, meaning the coordinates do not change with time. Then we'll get into equatorial celestial coordinate system, which is where most, where the real astronomers are. Essentially as the most used system. Effectively, it identifies everything on, stars, galaxies, whatever, based on certain things, certain points of interest on the celestial sphere. Then there's the ecliptic longitude, which is based on our solar system. So therefore, if you really like planets for some reason that are not going around other stars, the ecliptic system is the one that's you want to use, the most handy. And then galactic coordinate systems. If you're interested in only things within the galactic, within the Milky Way galaxy, specifically in relation to its dynamics, the galactic coordinate system is the most useful. All right, so let's get into this. Lecture Astronomical Coordinate Systems. So again, this is all basically based on the celestial sphere, which again was an abstraction by the Greeks. Now we understand that it is a 2D representation of a 3D universe. If you look at the Orion Nebula, for example, the Orion Nebula, the Orion constellation, the stars in Orion seem to be fairly close together, in the sky at least. But if you looked at the 3D, basically the direction, the radial direction outward, on average, the brightest stars are about a few hundred, even 1,000 light years apart. So they are really nowhere near each other. They certainly aren't gravitationally bound in any way whatsoever. Orion is an example of a constellation. And so astronomers at some point divided up the celestial sphere and quantitatively marked out where the constellation boundaries are. You can think of them as essentially celestial states. So when I say something is in the constellation of Orion, that there is a specific boundary that I'm talking about. I have yet to look into how these were developed, but effectively it seemed to me that there was some kind of gerrymandering going on, because constellation boundaries are in no way square. So yeah, really, it's kind of weird. Anyway, 88 constellations on the celestial sphere. This is a list of variables, related to the horizontal, equatorial, ecliptic, and galactic longitudes. these are going to be, so for example, when I talk about right ascension, that is designated as alpha. When I talk about declination, that is designated as delta. I didn't have time to put together a conversion system or put together a slide on a conversion system. So I'm basically just going to show you where they are on ye olde Wikipedia. And this is, and so it shows you how to use essentially celestial coordinate transformations to move from one coordinate system to the other and so forth. There are online tools that you can use to do this, but if you want to know how the math works, if you want to be able to calculate it by hand or write a code that can calculate it, then I will show you where those equations are located. So let's talk about the horizontal coordinate system. The horizontal coordinate system is based on your local position. And so what you envision is you are standing on a flat plane. And that plane is encapsulated by a hemispherical dome above your head. The point that is directly overhead is the zenith. The point that is directly below your feet is the nadir, although functionally that's really not all that important. And the line which moves, or that goes from due north through the zenith back down to due south, that is known as celestial meridian. The celestial meridian is important because it quite literally divides the sky into the eastern and western hemispheres. What that matters is that anything in the east is currently rising, meaning it's going to get higher in the sky as the night progresses. Once it crosses the meridian, it's going to get lower and lower in the sky, and it's going to set. If it's on the meridian, that is as high up as that object is going to get at your location at any point ever. So the coordinate system, and any coordinate system really, particularly when you're talking about a 2D surface, in order to define a unique position, you need two coordinate points. In this case, those are altitude and azimuth. Altitude is simply the angle to the object above the plane that you are standing on. So for example, if something were on the horizon or on the plane that you are standing on, then that would be 0 degrees. Zenith is 90 degrees, nadir is -90. So really the horizontal coordinate system ranges from 0 degrees to 90 degrees. So anything like this would be 45 degrees, 30 degrees, so forth and so on. Azimuth is defined as the direction due north, and that is 0 degrees. And then it increases eastward. So if you were looking due east, it would be 90 degrees. If you're looking due south, 180, due west, 270. The thing to note about the horizontal system, and this is why Hipparchus could only do a differential sort of catalog, is that, as you might expect, a star's altitude and azimuth are constantly changing. They are strictly time dependent, location and time dependent. So if you measure the altitude and azimuth of a star and then got on the phone or were doing a live stream with somebody else who is, say, in California, and you were to say, hey, HL Auriga is at 15 degrees altitude and 280 degrees azimuth, the person in California would not find HL Auriga at that point because for them, their local sky is going to be different than yours. And again, as soon as you give that give those coordinates over, depending on how precise they are, they may not even be accurate by the time you finish reading them off, because again, the star is moving over time. Equatorial system. Do apologize, this is a little bit messy. This is actually an overlay of both equatorial and galactic. Thing to notice here are the red lines, really. So you have the sun, and really think of that as actually the Earth. That orange point is actually the position of the Earth in this. And so declination is celestial latitude. Declination of 0 means that you are along the plane of the celestial equator. Celestial coordinates or equatorial coordinates are effectively or basically are analogous to geometric to geographic coordinates. So effectively, if you took the line of the equator of the Earth and expanded it out to the sphere, that line is now called the celestial equator. If you took the North Geographic Pole and went straight up, and when it hit the celestial sphere, that point would be the North Celestial Pole, and then same thing corresponds to the South Celestial. So declination is defined as 0 along the celestial equator, the plane of the celestial equator. It increases towards the north and is 90 degrees at the North Celestial Pole, and it is not negative 90 degrees south of the celestial pole. Typically, declination is given in terms of positive or negative numbers. However, it can also be written in terms of north and south. So a positive number corresponds to anything in the northern celestial hemisphere. Anything in the south corresponds to negative celestial declination. Right ascension. Right ascension is defined as 0 directly towards the vernal equinox. Now, that point is defined as the point on the celestial sphere where the sun's coordinates hit the celestial equator, and then while it is going up. So the ecliptic, because of the fact that the Earth's tilt is 23.5 degrees, the equatorial or the ecliptic plane or the zodiacal plane of the Earth, the zodiacal plane of the sun as defined by the orbit of the Earth going around the sun, that is tilted 23.5 degrees with respect to the celestial equator. And so if you were to look at the sun as a function of right ascension and declination, what you would notice is that the sun rises in right ascension and declination. It then sets, or it then gets to a maximum amount in declination of 23.5 degrees. And then as it increases in right ascension, it's going to decrease in declination until it's 0 again. And then if you keep going, it's going to be negative 23.5 degrees and then back to 0 again. Those points, the 0 where it's rising through the celestial equator, that is the vernal equinox. The point at which it's at positive 23.5, that is the summer solstice, the time of the summer solstice. As it's hitting the celestial equator going down in declination, that is the autumnal equinox. And then finally, when the sun is at negative 23.5 degrees in declination, that is the time of the winter solstice. So right ascension and declination are the two coordinate systems that we are basically going to use for the rest of the class. So getting a handle on those is of particular importance. The ecliptic coordinate plane or coordinate system, as I said, this is defined, or the reference point of this is the Earth's path around the sun. That path, or that plane that path demarks, is called the ecliptic. And so that is the 0 point of the ecliptic latitude, or beta in this case. So anything that lies within the ecliptic plane has a ecliptic latitude of 0. Directly perpendicular to that plane going north is 90 degrees, or the ecliptic north pole. Anything south of that is negative 90 degrees ecliptic south pole. Now, north and south in the solar system is a little bit kludgy. For the equatorial system, north and south are basically you can think of them as the northern hemisphere and the southern hemisphere. For example, if you're on the North Pole, then the only stars that you can see are those stars that are in the northern celestial equator, or northern celestial hemisphere. Same thing for the South Pole. For the solar system, north and south are defined as such. If you were to place yourself where you could see the solar system as a flat disk, and you notice the planets orbit around the sun in a counterclockwise direction, that area is considered north, or above the solar system, or positive ecliptic latitude. If you're on the other side and you look up and you see it going clockwise, then that is the south or below the ecliptic. Ecliptic longitude is defined exactly as right ascension is defined. It is pointed towards the vernal equinox. So longitude, and it increases to the west. Then finally we have the galactic coordinate system. Again, this is defined as the plane of the galaxy as marked out by the sun's orbit around the galactic center. And so galactic latitude is, again, 0 is anywhere along that plane. If you're north of it, in the same sense as the solar system, you are at positive values all the way to the North Galactic Pole, which is perpendicular to that plane at 90. And then anything below that is negative 90, or negative galactic latitude. Galactic longitude, instead of the vernal equinox as being the 0 point, it is the galactic center, which is located in the constellation of Sagittarius. That is the 0 point for longitude, and it increases as you go to the east. Next thing that I'm going to show is I'm going to use the program Stellarium, for the next part of this lecture. For the next part of this lecture, I'm going to be using the program Stellarium. It is free. The link will be in the description, and I also put out a link on Blackboard. I believe it's stellarium.org. Perfectly safe. Millions of people use it, so don't worry about it. What I'd like you to do is I'd like you to download and install that program onto your laptop. If you do have a Chromebook, that's probably going to be problematic later on in the semester, but there is a web-based version, so you can use Stellarium on your browser. However, the functionality is more limited. So I would highly recommend installing the program onto your own machine. At this point, this is the night sky at my location at Fairfax, Virginia, on January 28th, 2025 at 6:11 approximately in the evening, or excuse me, 4:11 in the evening. It uses a 24-hour clock, so basically add 12. So 16:11 approximately. So you can see the sun is fairly low on the horizon. Now, the way I got this, way this pops up is, and I think I need to remove my lovely face from this demo or this lecture, is I moved over to the left and this bar popped up. Just go to where you see the clock and its time and date window, or it's also F5 on your computer. And so you can change this. You can change this to really anywhere you want. So I can look at how the sun moves as time is roughly constant as a function of day, or I think it's the 28th. I can make it later. And so I'm actually going to change this so that we're looking at basically 8 o'clock tonight. When I go down here, if I scroll down to the left and this bar pops up, I'm going to hit this, the play button, to pause. So now the sky is stopped at that particular time. If I go down to here, and scroll over to the left, we're going to see what's known as the azimuthal grid, or I think letter Z. If you click that, what that does is that superimposes a horizontal coordinate system onto the night sky. And so you can see that this line here corresponds to 5 degrees, this line 10, 15, 20, 25. And if I click and move the mouse, I can scroll up, and ultimately you can look up and you're going to have to basically count. Like this is 30, 35, 45, 50, all the way up to 90 located right there. These lines going around, if we look here, the lines that are going straight up and down, but seem to converge or do converge at the pole, those are lines of constant azimuth. So we can see that if we If we go and scroll around and we go to due north, this has this is 0 degrees. This line corresponds to 0 degrees, and that is the line of the meridian. Well, on this side is 0 degrees. If I go to east, if I look due east, that line is 90. If I look due south, 180. And again, if I look due west, that is 270. Let's look at Venus. So Venus in altitude and azimuth at this particular time I can estimate it to be about 14 degrees in altitude and 257 degrees in azimuth. But I don't have to estimate. If you click on Venus, you get all of this lovely information. Where you want to look is azimuth and altitude right here. The first number is azimuth. It's positive 257 and 57 degrees, 42 minutes, 10.4 arc seconds. And then the altitude is plus 15 or plus 13 degrees, 58 minutes, 36 seconds. So I was pretty close, just eyeballing this thing. So that's Venus. And you may notice that after it says apparent. I'm going to leave this as an exercise to you why that value is apparent. What is it that's causing the altitude and azimuth to change with respect to where the star or object is actually located on the celestial? I'm then going to unpause this. And what you notice is that the altitude and azimuth number, as I've said before, constantly changes as time progresses. However, right ascension and declination do not. Those are absolute coordinate systems. Those are they are location independent and time independent. Let's go to a different object. Let's go to Jupiter. Jupiter has an altitude and azimuth of 4 hours, 39 minutes, plus 21 degrees, 38 minutes. Again, that is only true at my location in Fairfax at 8:01:01 Eastern Standard Time. So you can see that this is how, as it gets higher, altitude. I'm sorry. I think I read you the wrong numbers. The altitude of Venus is the azimuth of Venus is one. The azimuth of Jupiter is 169 degrees, 23 minutes, positive 72 degrees, 33 minutes. You can see that it is much higher up in the sky as the altitude suggests. Let's come back down. Go over here. Let's click off the azimuthal grid and click on the equatorial grid. You can see that the equatorial grid is slanted. And again, if you were to take the angle between the horizon and one of these lines of right ascension as it intersects the horizon, that angle would be 23.5 degrees. As you can see, the right ascension declination lines are tilted with respect to the horizon. And the reason for this, again, is the Earth's axial tilt. Or lines of declination run this way. They run from east to west. Lines of right ascension run north to south. You noticed before that when you looked at the zenith, using the horizontal coordinate system, basically a altitude of 90, there wasn't anything there. But if you look at the North Celestial Pole, you can see that little thing. And that is Polaris, the North Star. What is noteworthy is that the declination on today's date, I'll get into epochs later when I start talking about time in the next lecture. The declination is not true north. It is not 90 degrees. It is 89 degrees, 22 minutes, 32.3 seconds. Having a hard time saying that. Polaris is not, strictly speaking, due north, but for, back of the envelope types of things, it's good enough. If you see Polaris, that's basically the north. But if you wanted to set up a telescope, if you wanted to properly align an equatorial telescope or an equatorial mount, this is important. You cannot center it on Polaris. You actually have to center it slightly off of the Polaris's position because of the fact that it is not, strictly speaking, due north. And it also changes over a much smaller time scale with time, in that the 0 point, or Polaris's position in the sky is actually happenstance. The Earth precesses as it over time, meaning that its axial tilt, the north celestial pole, will move with respect to the stars with a period of about 26,000 years. So right now, it just happens that Polaris corresponds or is very, very close to the northern celestial pole. In about 13,000 years, that honor will be Vega's. Vega won't be as close as Polaris is, but it will be pretty close. And if we're around in 13,000 years, people will probably refer to Vega as the North Star. Again, you can see that if I were to choose Venus, Venus currently has a right ascension declination of 23 hours, 36 minutes, and negative 0 degrees, 35 minutes. So it's slightly below the celestial equator. Jupiter has a right ascension of 4 hours, 39 minutes, and a declination of 23 degrees, 38 minutes. Rigel has a right ascension of 5 hours, 15 minutes, and a declination of negative 8 degrees, 10 minutes. The constellation Orion is almost perfectly bisected by the celestial equator. So if you're in Antarctica, and you're there when it's nighttime, the 6 months of nighttime, all you would see is Orion's butt, basically from his waist upward or downwards. That's all of Orion you would see at any point ever. If you're at the North Celestial Pole, then you get to see the top half of him. And here again, if I let time progress, the right ascension and declination do not hold. Now, what about our friend H.L. Auriga? Well, my friend, and soon to be your friend. You can find H.L. Auriga using Stellarium. It is in the catalog. It is a well enough studied object that Stellarium is aware of it. So if you want to find anything using Stellarium, you can go over, again, going over to the left, and you can choose the search window, what basically looks like a magnifying glass with a star in the center of it, or F3. Come over here, and you can see I've already searched for it, but just to be clear, I can put in HLAUR, that stands for Auriga, the constellation of Auriga. Click on that, and then boom, it shows me where it's located. The V star indicates that it is a variable star, meaning that the brightness of the star varies with time. When I zoom in, you may notice there isn't a star there. That's not because Stellarium doesn't have it in its database, but it's because HL Auriga is a fairly dim star. It has a visual magnitude of 11. And what I have done with the settings is that Stellarium is only showing me stars or objects that are brighter than 6th. So it is a representation of what my human eye can see if I were in an area without light pollution. I can change that such that I can set the limiting magnitude lower so that more and more stars pop out. Now, you may have noticed that right ascension and declination are in hours, minutes, and seconds, as opposed to degrees, minutes, and seconds. And the reason for this is because right ascension effectively traces the movement of the sky with respect to the Earth. And so because of that, it can be used effectively as a clock. So let's look at the local meridian. And again, the local meridian is this green line here, which goes from south all the way up through the zenith down to north. And let's look at the star Rigel. Rigel, again, has a right ascension and declination, or right ascension of 5 hours, 15 minutes. Let me move this guy so that Rigel is effectively on the meridian. I'll get into what this means in the next lecture. But when a star is on the meridian, its right ascension is the local sidereal time. So you can see right here, right ascension is 5 hours, 15 minutes. If you go to the apparent sidereal time, 5 hours, 15 minutes. This star, Gamma Mon, has a right ascension of 6 hours, 16 minutes. So if I were to go over here and I were to advance the time by 1 hour, lo and behold, the star is now at the meridian. So what that means is that it has taken 1 hour to go from a right ascension of roughly 5 hours, 15 minutes to a right ascension of 6 hours, 15 minutes on the meridian. Another way to look at this is that, and so using this, one can get a rough estimate of how long it's going to take for something to move onto the meridian. So if I wanted to look at Mars, for example, and I wanted to look at Mars when it was as high up as possible, and I know that the right ascension of Mars at that time is 7 hours, 35 minutes. That tells me that I have to wait another hour and 20 minutes before Mars is on the meridian when it is highest up in the night sky. That is why right ascension is given in basically time units. I think that pretty much wraps up this today's lecture. And again, future lectures will be posted regularly every Sunday at some point during the day on Sunday. All right. I look forward to seeing you in class.